For a very broad class of the kinds of functions that we come across in physics, we can presume that they are what is called analytic, except possibly at some singularities, or at least within some region. So, at least within some range of values of our argument x, maybe near some point x0, we're presuming that our function f of x can be approximated arbitrarily well by a power series. For example, if we are looking round about the point where we're saying this x0 is 0, then our power series is a0 plus a1x plus a2x squared, and so on. For example, if the function was actually a parabola, we would just need the first three terms in this series with some numbers for a0, a1, and a2. But possibly this series goes on and on and on. Maybe it's infinite. Incidentally, we are using this notation here that we may have come across before called an ellipsis, and that simply means that we are omitting writing down some of the terms explicitly. Also, if we took a more general point rather than saying that x0 was equal to 0, we are saying that round about some other point, this function f of x we're presuming can be written in this kind of a form, where now our powers are x minus x0 that we're raising to a power. Taking the simplest case, where we are going to take x0 equal to 0 first, we're presuming we can write the power series like this. So let's figure out what these various numbers are, or how to deduce what they are from what else we know about the function. So, obviously, if we take x equal to 0, all of these terms completely disappear. So we're just left with a0. So we know, therefore, what a0 is. a0 is f of 0. What about a1? Can we figure out what a1 is from our knowledge of the function? Well, if we take the derivative of f of x with respect to x, then the derivative of a0 itself is just 0. The derivative of this term here is a1. And the derivative of this term here is 2a2 times x. The derivative of this term here is 3a3 times x squared, and so on. So, at the point x equals 0, these terms all disappear, and we're left just with this term. And so we've now found a way of figuring out what this coefficient is. So a1 is the derivative of f at the point 0. Now, remembering this here, what we're going to go on and do next is find the second derivative. So we're going to be taking the derivative of this expression. So here is that derivative, the second derivative now, and we had 2a2x when we just looked at the derivative itself. Taking the derivative of that to get our second derivative, we have 2a2, and then a bunch of other terms here. We can also write these, incidentally, using the factorial function. So again, at the point x equals 0, all of these terms disappear. These ones out here all disappear, and we're just left with this term here. And we can carry on like this. If we take the third derivative, we're taking the derivative of all of this expression. This term will disappear because it's just a constant. And we will end up having this term turn into simply 3 factorial a3, and so on. We could keep on going like this. So, continuing with this process, we can deduce what the values of all of these various coefficients are. So this was a0. All of this here is a1 times x. All of this here is a2 times x squared, and so on. And all of this here is an times x to the power n, and so on. So what we are saying is that if we know the function and can evaluate all its derivatives near to a point, here the point x equals 0, then we can also write the function out as a power series. Now, we have to be somewhat careful with this. If we choose x to be too large, it's possible that this power series may not converge. So we always have to be careful with a power series that it may only be valid for some range of x. But nonetheless, we can write out power series usefully for many functions, and sometimes the so-called range of convergence is not constrained. It may be very large or possibly even infinite. Now, instead of doing this process round about x equals 0, if we did it instead round about some other point, x equals x naught, then with our presumed power series that we're trying to find these coefficients for, we can in fact proceed in exactly the same kind of way, and we will get what's called the Taylor series. And this here is the Taylor series. It's essentially the same as the Maclaurin series, but instead of everywhere we have x here, down here we have x minus x naught. So it's x minus x naught raised to all of these powers. So let's look at some example power series expansions of common functions. The function 1 over 1 minus x, if we carefully work that out, we will find that that one is 1 plus x squared plus x cubed, and so on. Again, this will only work for some range of x, but for small x, this will work fine. The exponential of x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, for its power series. The power series for the cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And the power series for sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus the next term, and so on. So note that the signs of these terms are alternating in the cosine and sine expansions. And if you check it out, you can in fact use Euler's formula to deduce these power series from this one here. Now, the other very important point about power series, especially in physics and in modeling systems of various kinds, is the idea of using power series for approximate results. So Maclaurin and Taylor series allow us to make approximations for small ranges around about some specific point. So here are some examples for small x for some functions. And these are the approximations which are valid to so-called first order in x. And it's another important point about this whole notion here is that it helps us establish what we call the order of an approximation. So a first order approximation to 1 over 1 plus x from our power series that we were looking at before, we could evaluate the power series of 1 over 1 plus x. And that is 1 minus x to first order. So as you start to increase x from 0, the first thing you will see is that this function corresponds to something that starts out decreasing linearly in proportion to x. So the first order approximation to this function here is one that shows a linear decrease with x, just to start with. Similarly, this expression is one that comes up quite often, and we like to know an approximation for it for small x, and the answer to that is 1 plus x over 2. For the exponential function, again, the small x approximation to that is 1 plus x, the power series expansion, the first term to the power x to the power 1. And the logarithm of 1 plus x, which is related to this here, is just x to lowest order, to first order in x. Sin x to lowest order in x is just x. Tan x is just x. So all of these are what we would call first order approximations to the functions. Note incidentally that cos of x is an example of something where the lowest order of approximation, at least the one that depends on x, is not first order. The lowest non-zero order is actually second order. So the lowest order approximation to cosine of x that actually depends upon x is 1 minus x squared over 2.